Alrighty, so I should be recording now. So update, it's all about atoms and periodic properties. Core concept is how we develop the model of the atom, and we start with some history on that. So we've got the ancient Greeks, where Democritus was the first person to kind of imagine what an atom might be, because he theorized that there must be some particle that's no longer divisible if you go small enough. And then Plato and Aristotle disagree. They're like, oh no, you can divide forever. Don Dalton picked this back up, or he was the most recent one to first think about atomic theory. And he did this because he was looking at chemical reactions and he saw a few different things, but he also figured that in order for chemical reactions to happen, there must be atoms. So, in particular, this chemical compounds are made of atoms in specific integer ratios, because if chemical reactions have to happen in whole numbers, or your chemical compound is just ratios of numbers of elements, then those elements must have something in them that is not dividable. And we call those atoms. So a matter has indivisible atoms. He theorized a few different things that maybe were or were not correct. The ones that were not correct were an element made up of identical atoms. We know that is false now, because isotopes are true and exist. So isotopes kind of contradict this idea of an element being made of identical atoms. But atoms are neither created nor destroyed is true. Chemical compounds, this is just an observation, so I'll draw an eye. And then different elements have different masses. We see that as being true. And yeah. This atoms are neither created nor destroyed also goes along with one of our um, principles of thermodynamics, where energy is neither created nor destroyed. Same with matter is neither created nor destroyed. So there's that. Some experiments that led to the discovery of different parts of the atom include the cathode ray experiment by J.J. Thomson, where he basically shot a beam of whatever electricity is made of from the cathode to anode plates in a air restricted or vacuum. Yeah, in a vacuum, these cathode rays usually had a vacuum pumping the air out, so they knew that it was not air that was making the light, essentially. Using this and this setup where he used like magnets and charged plates, he was able to figure out two things: the fact that whatever the beam is made up of is negatively charged, and that they can be deflected by a certain amount. So he used the charge that he calculated and the amount that they were deflected to figure out the charge to mass ratio. And this beam that he was sending off was later discovered to be electrons, because in very simple terms, electricity can be defined as the flow of electrons. Then we have Robert Milken. He's the one who kind of took the cathode ray experiment and decided to figure out what the actual charge and mass is of the electrons. And he did this by using oil droplets and still having that sort of electrical discharge between two plates to see how much these oil droplets that have now been charged with electrons resist gravity. So we know the amount of gravity, and then we can see how much they resist gravity. That allows us to calculate the mass. And because we can calculate the mass and we know the mass charge ratio, we can calculate the charge as well. Then, of course, there was like, well, then what is an atom? We've got the atoms are indivisible, and we've got that electrons are very small and have a very small mass and have some charge. But because the electrons are negatively charged and atoms are neutral, there must be some positively charged matter, which Thomson proposed being like pudding that surrounds the electrons. Ernest Rutherford disproved Thomson's plum pudding model because he discovered that there are nuclei in the middle of the atoms. He did this by shooting a radioactive alpha particles from a radioactive source through a very thin gold foil and saw that a lot of them went straight through, meaning the majority of the space was empty or, yeah, empty space. And then a few of them deflected at some pretty large angles, which meant they were hitting something pretty small. And because alpha radiation is positive, they were hitting something positive. Because if they were hitting something that was negatively charged, then they wouldn't really move too much or they'd um, kind of be attracted to it. These positive charges were called protons, and for a while we thought that the nucleus was made up purely of protons, but then James Chadwick proved that there are neutral items within the nucleus, which he called neutrons. That gives us our view of the atom, where we've got protons, neutrons, and electrons. The atomic number is the number of protons in a nucleus. This is something that you should 100% know. Atomic number, number of protons. You can find this on the periodic table. If you look, it's basically what we define that like the elements as. So it's like their little number. So beryllium is 4. That's the number of protons that are in beryllium. Arsenic is 33. There's 33 protons in arsenic. Mercury is 80. There's 80 protons in mercury. So that's just important that you know how to tell how many different protons there are just based on the periodic table, because that's what distinguishes the different elements. In a typical neutral atom, the number of protons is going to be the same as the number of electrons. Because, right, if there's no charge, then the number of positive charges and the number of negative charges will be the same. So that's what this part here is saying. Then isotopes are just when there's different number of neutrons, which changes the weight slightly. So these are all isotopes. I wonder if I have a laser pointer. So these are all isotopes of the same atom or of the same element. Important thing to know in the history part is just the order in which things were discovered. I won't be asking anything about specifics on how they were discovered because that's just something that you probably won't be needing that much in your life. But do know that we discovered the fact that atoms exist first, and then we discovered that there's something we're calling electrons, and we can have the charge mass ratio, which we then discovered charge mass ratio. So we discovered the atom, then we discovered the electron, then we discovered the nucleus, or the protons, and then finally we discovered the neutrons in the nucleus. So yeah. So order of discovery, atom, electron, new. Oh, we have just some more symbols on things. I'm gonna skip this because it's not super important. Mass number is the number of protons plus neutrons, and you get the mass number from the bottom part of the periodic table. Okay, mass number is specific for the isotopes because that's what that's there. The atomic weight is the average of the mass number of naturally occurring isotopes, which is where we get these kind of half fraction numbers here because there's some that are like 50 and some that are 51, or one that's easier. For hydrogen, we have most of them that are like 1 because there's only like one proton in there, and some will be like 2 because there's a proton and a neutron. But you don't really need to know that too much. Do know mass number is number of protons plus neutrons, just like be able to memorize that, and that the atomic number is the element number, and that's how we distinguish them. We can kind of skip this. Basically, atoms shouldn't be able to exist with a common mechanical theory that we have, or like physics that we know of. So we need a new theory, which is where we get quantum mechanics, because Something so small as an atom and their electrons act different than things on a larger scale. This is Planck's equation that Max Planck introduced, and he also has his constant here. So this is his equation, and that's his constant. Just know the equation. I acknowledge that we did calculations in class, and I realize now that you guys don't really need to do that, so we won't be doing that. But do know that Planck's equation was used to calculate a photon's energy using its frequency and then Planck's constant. So this is the main thing. Know that it's calculating energy. That E stands for energy. Similarly, Einstein came up that light's made up of quantized photons, and then the higher frequency, the more energetic they are. I think yeah. Is there a thing later on? Yeah, there is. Okay. We talked about black body radiation, which you don't really need to know. It's just part of the history of how we discovered stuff. Black body radiation is basically like a light bulb or a hot coal, something that has continuous distribution because it has multiple elements and it depends on the temperature. Then we have the line spectrum, also known as the Balmer series or emission spectrum. This is a video that we watched in class where we saw that there's different elements in this lamp here, and then we pass it through. In this case, it's a slit in a prism. For us, it was a spectroscope, which is a special type of film. And then that separates out different lines. We see the Balmer's theory, Balmer's lines for hydrogen here, where we get basically three different colors for hydrogen based on the energy levels that that the orbit has. And that's where we get the Bohr's theory of there must be different orbits and the electrons can only exist within those orbits. Granted, we know that now that's where they're most likely to be found because electrons are really weird. Um, but basically, when it jumps up or down, it'll either absorb or release energy. So if we're jumping down, we're absorbing, no, releasing. I don't want to type all that. I don't want to write all that. Weapon energy means absorb. And then when we're moving down in energy, that's where we get our radiation. And that's where the spectrum comes from because each atom or element will have its own kind of orbitals, and then those orbitals will determine basically how much energy it will release when um, yeah. Where were we? Radiation is emitted as absorbed. Yep, when it's going down in energy, it's losing energy, so it releases a photon. That's just something, yeah. You should know that when an electron jumps down to a lower orbit, it will release a photon, which is just a packet of energy because it's moving from higher to lower energy. So it's losing energy. But also know that these Balmer lines or emission spectrum or line spectrum, whatever, they're called different things. Balmer lines is specific to hydrogen. So I'll usually call it emission spectrum or line spectrum. But that is very specific to an element and it will never change. It doesn't change for temperature, it doesn't change for like amount of element or anything like that. It's constant because it's intrinsic to the way that the electrons are set up. I won't be doing any example calculations. The highest energy, just know that as you get smaller in wavelength, it's going to be moving faster. So if you come over here to like the visible light spectrum, we see here the wavelengths where the violet is like in the 30 to 300 to 400 nanometers, and the red is from the 600 to 700 nanometers, and violet is higher in energy than the red color light. So as those wavelengths are smaller, they're moving faster and they have more energy. And as they are bigger, they're moving slower and they have less energy. So just good rule of thumb to know that smaller wavelength, more energy. Larger wavelength, less energy. So then if we wanted to like calculate this or figure out which one has the highest energy, we'll just look at the one with the smallest wavelength, in which case is the 110. And that's something you should know. This is Lewis de Broglie equation. Again, I won't be doing any calculations with it because we figured out that you guys don't need that. But do know that it's used to calculate the wavelength using the mass and speed of the wave or particle. So just know what it's for. It's called de Broglie's equation. It's for finding the wavelength of something. That's calculations. Young's two-slit experiment showed that electrons have a duality of light and matter, just like so it acts as like a particle and it acts like a wavelength. I think that's about as far as you need to know. These are just further more in depth on the way that the wave nature of electrons and how like Schrodinger helped develop these systems, and he kind of developed this visualization technique for identifying where electrons will probably be existing, which is what we call our kind of orbitals, even though they're technically delocalized and they don't really stay to the rules all that much. These you don't really need to know. Principal quantum number is just energy level, and then all the rest is something you only really need to know if you're doing higher physics. But do know the shape of the orbitals. So know that p orbitals are shaped like this little infinity sign, and s orbitals are shaped like a circle. So if I can get my annotate here. So see how it's kind of like an infinity sign? And then also because of the Pauli's exclusion principle, each of these will only hold two electrons, which means for the s orbital, we only have a total of two electrons, but for here, we have a total of six because we have two in each of the three p suborbitals. And the main thing to know here is holds two electrons, p system holds six. Right? Because all three of these combined add up into the six. Cool. This is just this each orbital and how many electrons they hold. Again, S is 2, P is 6. If you get up to D, you have 10, and then F is 14. Electron configuration, I know we probably won't be including it that much. Pauli exclusion principle is just the fact that there's only two electrons per orbital. Um, yeah, writing the electron configuration. The thing that I had messed up with here was that I recalled it as principal or period being the same number, but it's actually the D and P's actually have a lower number. So in the example of the periodic table, let me see if I can open this up better. These all follow the period up until the 3, but then once you hit here, this is actually like 3D here. And 4D, even though it says 5. But all the rest is the same as I taught you guys. Know that the rows are the period and the columns are the groups. So right this way is a period, and then up and down is a group. Let's see if I can do the spotlight. This way is a period, and that's a group. Each group shares very similar properties. That's why we have their own names for them, like alkali metals, alkali earth metals, things like that. And also know that they share the same number of valence electrons. That's something that we're going to definitely use. If not for the chemical bonds, it's going to show up somewhere on a practice homework exam, something like that. Because basically, as you step over, at least skipping over the d orbitals, it's one valence electron, two valence electron, then your full s orbital, but it's not held tightly. Then your p orbitals, three valence electrons, four valence electrons, five, six, 7, etc. You can even label the top if you wanted to. Do 1, 2, 3, 4, 5, 6, 7, and then finally 8, which is where they want to be. If they are past this, basically like 4, they're going to try and be getting up to 8. If they're below that 4 and they're below having 4 valence electrons and it being half filled, then they're most likely going to want to lose their electrons. Unless bonding is going to be really easy. That's the main thing to know. A and B group are just where they are in the periodic table. The A ones are the ones we'll use the most, and the B group is most of these middle transition metals. Those are examples. That's the periodic table. This is kind of what we're talking about with the 1 to 3 outer electrons, which is up to the B, wanting to lose their electrons, and then anything other. I like to think of it before 5, 4, but yeah, 5 is definitely gonna want to hold on to. 4 is kind of in the middle, which is actually what makes carbon such a wonderful thing for life, because it's happy to share 4 electrons or it's happy to bond and things like that. And these are just electron dot configurations, which you don't need to know. For examples, and then that is the end of this lecture, and I will do the next one soon.